All right, this is our last example, example 13. Determine whether the following integral converges. We've got arctan of x over 2 plus e to the x, and we are integrating from 0 to infinity. All right, so let's look at the graph of arctan for a second. Arctangent has two horizontal asymptotes. So this would be negative pi over 2 and positive pi over 2. And then arctangent does this little S sort of curve like that. That's arctangent. Okay, so arctangent of x is definitely always between 0. Sorry, arctangent of x is always between negative pi over 2 and pi over 2. But because of our integral, we are only looking for values of x, or considering values of x between 0 and infinity, which means we really only have to say this at our strictest, that arctan of x for x greater than 0 is between 0 and pi over 2. So from this picture here, I'm going to go ahead and just say arctan of x is greater than or equal to 0, but less than or equal to pi over 2. In fact, we know that it's strictly less than pi over 2. It never actually reaches there. But again, when you're comparing an exclusive inequality or an inclusive inequality, if it's true and it's okay to include that, like saying that this is or equal to, it's an or statement. It doesn't mean both have to be true. So although it's not always true, that's okay. So we'll start with that inequality. Arctan of x is between 0 and pi over 2. So now that I have that inequality, I'm going to try and build the integrand that we have. So from this inequality, if I wanted this middle piece, to match this, I would have to divide by that 2 plus e to the x. Now 2 plus e to the x is a positive number, and it's greater than 1, so my inequalities will all stay the same direction. No flipping or anything like that. So this will be 0 divided by anything is 0. Then we'll have our arctangent of x divided by 2 plus e to the x less than or equal to pi over 2 divided by this, so 2 plus e to the x. Okay. So now, what we have here is not terrible, but not a great inequality. Because this top piece right here, it seems a little bit complicated to work with. But here's the nice thing. If this 2 right here, if we just got rid of this 2, so for instance, let's just write this as pi over 2 plus e to the x. I'm getting rid of this multiplicative 2. What did I do to the denominator? I made it smaller, right? I removed this 2. This denominator is twice as large as this denominator. Well, if your denominator gets smaller, as we did from here to here, that results in a fraction that overall is larger. So if we remove that multiplicative factor of 2, then we can say that the result of that removal is greater than the previous. And furthermore, we can do it again. If I just subtract this 2, if I just erase this 2, that has a result of making the denominator smaller. It's not twice as small, it's just 2 less than it was before. Regardless of that, it results in a fraction that overall is larger. So a fact here that's important to know, and you all know this, but it really becomes a really useful thing to think about, and it's a guiding principle for these inequalities. Essentially, smaller denominator results in a larger fraction. So let me say, another thing you can do is if you do a larger numerator, obviously we still get the same thing, larger fraction. If we have a larger larger denominator, this results in a smaller fraction. And you can also achieve a smaller fraction by making a smaller numerator. So using these two things, you can manipulate a starting inequality to hopefully obtain an inequality that is useful for evaluating the given integral. So you can use these ideas here. Again, you should all know all this results, but they're not always in the front and center of your mind. But they should be when you're manipulating these inequalities. All right, so it looks like at the end of the day, the inequality that we're going to use is 0 is less than or equal to the arctangent of x over 2 plus e to the x, which is less than or equal to pi over e to the x. So these two inequalities here, they are, true, but they're not ultimately what we wanted because we have to integrate this one, more or less, or compare it. So we want it in its simplest form. So we just take the parts that we need, our integrand compared to a simpler function, and the fact that they're both not negative. So that's our inequality. All right, let's go ahead and write our comparison now. Since this inequality is true, and the integral from, what are we at, 0? It's from 0 to infinity of pi over e to the x dx converges. Why do we know this converges? Well, this is, we can go back specifically to example 1. And if we go back all the way to example 1, the integral we have here can just be rewritten as 1 over e to the x. And now, that's not pi, right? I know that that is not equal to pi over e to the x, but here's the thing. If this integral converges, that means it's equal to a finite number. So this is equal to some number. Okay, we don't know what that number is. So if I multiply this side by pi and this side by pi, pi times a number is still just another number that is less than infinity. Therefore, this one also converges. So, yes, it doesn't perfectly match, but it matches enough for us. So that's good. So example 1. So since that inequality and that integral converges, by comparison, so must the integral from 0 to infinity arctan of x over 2 plus e to the x dx. And there we have it.